Hello everyone, welcome back to the channel. In today's lecture, we are going to learn one of the most powerful and important concepts in object-oriented programming, known as the interface. This concept is widely used in real-world software development, enterprise applications, and modern system architecture. Understanding interfaces clearly will help you write clean, flexible, and professional-level code. Let us begin by understanding the basic idea behind an interface. An interface is a contract that defines what a class must do, but not how it will do it. In other words, an interface contains only method declarations, not implementations. It describes behavior, not logic. When a class implements an interface, that class must provide the full implementation of all the methods defined inside the interface. To understand this in simple language, think of an interface as a rulebook. The rulebook lists the rules that must be followed, but it does not tell how each person will follow them. Similarly, an interface lists methods that must exist, but each class decides how to implement them. In object-oriented programming, interfaces are mainly used to achieve abstraction. Abstraction means hiding internal implementation details and showing only the necessary functionality to the user. Interfaces provide complete abstraction because they do not contain any method body. The user interacts only with the interface and never with the actual implementation. Now let us understand why interfaces are needed. As applications grow, they become complex. Software systems may contain thousands of classes and multiple developers working on the same project. If classes depend directly on each other, the system becomes tightly coupled. In tightly coupled systems, a small change in one class can break many other parts of the application. Interfaces solve this problem by creating loose coupling. Instead of one class depending on another concrete class, it depends on an interface. This means the implementation can change at any time without affecting the dependent code. For example, consider a payment system. Today, the application may support credit card payments. Tomorrow, it may need UPI, net banking, or digital wallets. If the application code directly depends on a credit card class, changing the payment method becomes difficult. But if the application depends on a payment interface, new payment methods can be added easily without modifying existing code. This is one of the biggest advantages of using interfaces. Now let us look at a real-world example to understand this concept more clearly. Think about a mobile charger. The charger provides a specific interface, a USB connection. You do not care how electricity flows inside the charger or how it converts voltage. You only know that when you plug in your mobile, it charges. Different charger companies may use different internal circuits, but the interface remains the same. In this example, the USB standard acts as an interface, and different charger manufacturers provide their own implementation. This is exactly how interfaces work in software systems. In programming, interfaces act as a communication bridge between different components of a system. One component knows what methods are available, but it does not know how they are implemented internally. This separation improves system design and makes applications easier to maintain and extend. Now let us discuss what an interface can contain. An interface can define method declarations, property declarations, events, and indexers. However, it cannot contain fields, constructors, or method implementations. This strict rule ensures that interfaces remain pure contracts and do not store state. Because interfaces do not contain implementation, multiple classes can implement the same interface in their own way. This allows polymorphic behavior in programs. Polymorphism means one interface, many implementations. When a program calls a method using an interface reference, the correct implementation is executed at runtime. This is extremely powerful in designing flexible systems. Interfaces also support multiple inheritance indirectly. Many programming languages do not allow a class to inherit from multiple classes due to ambiguity. However, a class can implement multiple interfaces. This allows a class to inherit multiple behaviors without conflicts. For example, a class can implement interfaces such as printable, loggable, and savable at the same time. Each interface represents a specific capability or responsibility. This design follows the principle of separation of concerns. Each interface handles one responsibility, making the system modular and clean. Another important concept related to interfaces is standardization. Interfaces define standards in large projects. When a team designs an application, interfaces are often created first. Developers then implement these interfaces independently. This allows multiple team members to work simultaneously without conflicts. For example, one developer may define service interfaces, while another developer implements them. As long as the contract is followed, integration becomes smooth. Interfaces also play a critical role in framework and library development. Most modern frameworks expose interfaces instead of concrete classes. This gives developers freedom to customize implementations while using the same framework structure. Now let us understand interfaces from an architectural point of view. In layered architecture, interfaces separate layers such as user interface, business logic, and data access. The business layer communicates with the data layer through interfaces. This means the database can change from SQL to NoSQL without affecting business logic. This design is widely used in enterprise applications, microservices, and cloud-based systems. Interfaces also make unit testing easier. When testing a class, developers can replace real implementations with mock implementations. This allows testing logic without depending on databases, APIs, or external services. Because of this, interfaces are considered essential for test-driven development. In summary, the interface is not just a programming feature. It is a design philosophy. It encourages clean architecture, loose coupling, flexibility, scalability, and maintainability. Understanding interfaces deeply is a major step toward becoming a professional software developer. In enterprise software, applications are divided into multiple layers such as presentation layer, business layer, and data access layer. These layers should not directly depend on each other's implementation. Instead, they communicate using interfaces. For example, the business layer should not directly access database classes. It should depend on repository interfaces. This allows the data source to change without affecting business logic. This concept is the foundation of clean architecture. Clean architecture follows one simple rule. High-level modules should not depend on low-level modules. Both should depend on abstractions. Interfaces provide these abstractions. Because of this, interfaces are placed at the center of the system design. Now let us understand how interfaces help in dependency injection. Dependency injection is a technique where objects are provided to a class instead of being created inside it. Interfaces make this possible because the injected object only needs to follow the interface contract. This improves flexibility and testability. During testing, developers can inject mock implementations. During production, real implementations are injected. The main code remains unchanged. This is widely used in modern frameworks. Interfaces also help in designing service-based architecture. Each service exposes its behavior through interfaces. Other services communicate through these contracts, not through direct implementation. This approach improves reliability and scalability. Another important use of interfaces is in API development. APIs expose behavior but hide implementation. Internally, interfaces ensure that API logic can evolve without breaking existing clients. This ensures backward compatibility. Interfaces also encourage the use of solid principles, especially the dependency inversion principle. According to this principle, code should depend on abstractions, not on concrete implementations. This principle is considered a foundation of professional software engineering. Now let us compare interfaces with abstract classes conceptually. Both interfaces and abstract classes support abstraction, but interfaces provide complete abstraction. Abstract classes allow partial implementation. Interfaces define what must be done, while abstract classes can also define how it is done. In real-world architecture, interfaces are preferred when flexibility is required, while abstract classes are used when shared logic is needed. In modern development, interfaces are more commonly used because they provide higher decoupling. Another advantage of interfaces is reusability. The same interface can be implemented across multiple systems, platforms, or services. This allows organizations to reuse design standards. Interfaces also improve readability. When a developer reads an interface, they immediately understand what functionality exists without reading internal logic. This improves communication among developers. However, interfaces also have limitations. They cannot store state, they cannot contain fields, and they require full implementation. This can sometimes increase the number of files in a project. But in professional development, clarity and maintainability are more important than file count. Knowing when to use interfaces is also important. Interfaces should be used when behavior may change, when multiple implementations are possible, and when testability is required. They are ideal for external services, data access, payment systems, logging systems, and notification systems. Interfaces may not be necessary in very small applications, but even then, understanding them is crucial for career growth. In real enterprise systems such as banking, healthcare, e-commerce, and cloud platforms, interfaces are used extensively. Without interfaces, such systems would be impossible to manage. Interfaces act as the backbone of modern software architecture. They define communication rules, enable scalability, support testing, and ensure long-term maintainability. To conclude, an interface is far more than a programming keyword. It is a fundamental design concept that separates what a system does from how it does it. Interfaces allow software to grow, adapt, and evolve without breaking existing functionality. Mastering interfaces means mastering software design. Hello everyone, welcome back to the channel. In this lecture, we are going to understand how interfaces work in real-world applications using a simple and practical example. Until now, we have discussed the theoretical concept of interfaces, such as what an interface is and why it is used in object-oriented programming. Now we will move one step further and convert that theory into actual program logic so that the concept becomes very clear and easy to understand. Let us begin by understanding the real-world scenario. In many applications like online shopping websites, banking systems, ticket booking platforms, and mobile payment apps, users are given multiple payment options. A user may choose to pay using a credit card, UPI, net banking, or a digital wallet. Although the payment methods are different, the basic operations remain the same. Every payment system must support making a payment and processing a refund. This clearly shows that there is a common behavior shared by all payment methods. Whenever we identify common behavior in object-oriented programming, the best solution is to use an interface. An interface is used to define this common behavior. In our example, we create an interface called iPayment. This interface defines what actions a payment system must perform, but it does not explain how those actions are performed. Inside the iPayment interface, we declare two methods, make payment and refund. These methods contain only declarations and no implementation. There is no logic written inside the interface, no method body, and no business rules. This means the interface acts as a contract. Any class that wants to behave like a payment system must strictly follow this contract and implement all the methods defined in the interface. This design brings abstraction into the system. Abstraction means hiding internal details and exposing only essential functionality. The interface tells the application that payment and refund operations are available, but it hides how those operations are executed internally. The actual logic is written inside the classes that implement the interface, not inside the interface itself. After defining the interface, we create a class called credit card payment. This class implements the iPayment interface. Because it implements the interface, it is mandatory for this class to provide implementations for both make payment and refund methods. Inside these methods, we write logic related to credit card transactions. In real-world systems, this logic may include card number validation, communication with bank servers, OTP verification, and transaction security checks. For learning purposes, we simply display messages indicating that the credit card payment and refund have been processed successfully. Even though the logic is simple here, the structural design remains exactly the same as in real enterprise applications. Next, we create another class called UPI payment, which also implements the same iPayment interface. This class again provides implementations for make payment and refund methods, but the logic written inside these methods is related to UPI transactions. The method names remain exactly the same as defined in the interface, but the internal behavior is completely different. This shows that different classes can implement the same interface in their own way. This concept is known as polymorphism, where one interface supports multiple forms of behavior. The most important part of this example comes when we use the interface in the main program. Instead of creating objects directly using credit card payment or UPI payment classes, we create a reference variable of type iPayment. This is a very powerful concept. By using an interface reference, the main application does not depend on any specific payment class. It only depends on the interface. At runtime, the interface reference can point to any class that implements the iPayment interface. When the interface reference points to the credit card payment object, the credit card payment logic is executed. When the same interface reference is later assigned to the UPI payment object, the UPI payment logic is executed. The code in the main program remains exactly the same. Only the object assigned to the interface changes. This behavior is called runtime polymorphism because the decision about which method implementation to execute is made at runtime, not at compile time. This design has huge importance in real-world software development. Today, an application may support only credit card and UPI payments. In the future, the company may want to add wallet payments, QR payments, or even cryptocurrency payments. With interface-based design, no existing code needs to be modified. Developers only need to create a new class that implements the iPayment interface. The main application continues to work without any changes. This makes the system flexible, scalable, and easy to maintain. From an architectural point of view, this design follows the dependency inversion principle. According to this principle, high-level modules such as the main application should not depend on low-level modules such as concrete payment classes. Instead, both should depend on abstractions. In our example, both the application and the payment implementations depend on the iPayment interface. This reduces tight coupling and improves system stability. This same pattern is widely used in professional software systems including payment gateways, banking platforms, e-commerce websites, cloud-based services, and microservice architectures. Interfaces allow developers to write clean code that can evolve over time without breaking existing functionality. They also make unit testing easier, because mock payment implementations can be used instead of real payment gateways during testing. To summarize, the payment system example clearly demonstrates the real power of interfaces. An interface defines what the system can do, while implementation classes define how it is done. The main application communicates only with the interface, not with concrete classes. This separation of responsibility results in abstraction, polymorphism, loose coupling, easy maintenance, and future scalability. This is why interfaces are considered one of the most important and powerful concepts in object-oriented programming and are heavily used in real industry-level applications. Hello everyone, welcome back. In this lecture, we are going to understand the complete interface implementation and runtime polymorphism flow using the architecture diagram shown on the screen. This diagram represents how an interface works internally in C# and how different classes interact with each other during program execution. By the end of this explanation, you will clearly understand how abstraction, interface implementation, and runtime polymorphism happen step by step in a real application. Let us start from the top of the diagram. At the top center, we can see the interface iPayment, which is labeled as the contract. This interface defines two methods: make payment and refund. These methods do not contain any logic. They only define what operations must be supported by every payment method in the system. This means the interface does not explain how the payment is processed or how the refund is handled. It simply declares that these operations must exist. This is the pure form of abstraction, where implementation details are completely hidden. Now, if we move downwards in the diagram, we can see two concrete classes: credit card payment and UPI payment. Both of these classes implement the same iPayment interface. This means they are forced to provide implementations for the make payment and refund methods. Although the method names are exactly the same, the internal logic written inside these methods is different. Credit card payment contains logic related to card transactions, while UPI payment contains logic related to UPI-based transactions. This clearly demonstrates the concept of one interface having multiple implementations. The dotted arrows labeled implements show the relationship between the interface and the concrete classes. This relationship indicates that the classes are bound to the interface contract. If any method declared in the interface is not implemented by the class, the compiler will generate an error. This ensures consistency and standardization across the system. Now let us focus on the middle portion of the diagram, where we see the program class, also called the client or main method. This part represents the application layer. The most important point to observe here is that the program class does not directly depend on credit card payment or UPI payment. Instead, it creates a reference variable of type iPayment. This means the application depends only on the interface, not on the concrete implementations. This design is extremely important in professional software development. When the program execution starts, the interface reference is first assigned to a credit card payment object. This step is shown in the diagram as instantiate and call credit card. At runtime, the interface reference points to the credit card payment object. When the make payment and refund methods are called using the interface reference, the credit card implementation is executed. Even though the reference type is iPayment, the actual method executed belongs to the credit card payment class. This behavior is known as dynamic binding. After this, the diagram shows a reassignment of the interface reference. The same iPayment variable is now assigned to a new UPI payment object. This step clearly demonstrates that one interface reference can work with multiple implementations. When the payment and refund methods are called again, the UPI-specific logic is executed. The code inside the main method remains unchanged, but the behavior of the program changes based on the object assigned at runtime. This is exactly what we mean by runtime polymorphism. The same interface method call behaves differently depending on the object it refers to during execution. The decision about which method implementation to execute is made at runtime, not at compile time. This gives flexibility to the system and allows behavior to change dynamically. At the bottom of the diagram, we can see the console output blocks. These outputs clearly show that different messages are printed for credit card and UPI payments, even though the same interface methods were used. This proves that the interface does not control the logic, it only defines the structure. The actual behavior depends on the concrete class. From an architectural point of view, this entire flow follows the dependency inversion principle. The high-level module, which is the program class, does not depend on low-level modules like credit card payment or UPI payment. Instead, both depend on the abstraction, which is the iPayment interface. This reduces tight coupling and makes the system easy to extend and maintain. Now imagine adding a new payment method in the future, such as wallet payment or crypto payment. In this architecture, no changes are required in the program class. We only need to create a new class that implements the iPayment interface. The existing code continues to work without modification. This is known as the open-closed principle, where the system is open for extension but closed for modification. This diagram represents how real enterprise applications are designed. Payment gateways, banking systems, e-commerce platforms, microservices, and cloud-based systems all follow this same interface-based architecture. Interfaces act as a bridge between the application layer and the implementation layer, ensuring flexibility, scalability, and clean code structure. To summarize, this architecture diagram visually explains how an interface acts as a contract, how multiple classes implement that contract, and how runtime polymorphism allows the same interface reference to execute different implementations dynamically. This is one of the most powerful concepts in object-oriented programming and a fundamental building block of professional software design.